Hello, it's Keith here, and this is the first in a new series of assembly programming tutorials, this time on the PDP-11. Now, the PDP-11 might be something you've not heard of, and that would be perfectly understandable. It's a really old, by the normal standards of the systems I do, server processor. It was built into a processor board that consisted in a large machine sort of like this. So it's not something you're really likely to have come across if you're in the same age bracket as I am. Now there's two reasons I've decided to cover this. The first one is that one of my Patreon backers is a big fan of the Russian UKNC machine, which was a home or educational computer released in Russia in, I think it was the 80s. And this was based on the same processor. They sort of miniaturized the processor, kept the exact same compatibility, and then used that as their CPU. So that's the first reason. But looking at the PDP-11, you really start to notice something quite interesting, and that's that a lot of the things that were developed with the PDP-11 actually sort of continued on to the later processors. So you'll see things in the PDP-11 that carried on through to the 68000 series, for example, and I believe also the 8086 and the 6809. That when that was developed, they even sort of went so far as to say they were trying to make a sort of 8-bit version of the PDP-11. So I think it's a really interesting processor, not just because it's a good way of seeing where a lot of sort of modern processors got their original ideas from, but also because in some places it works quite differently to others. Now the first one of these is Octal. Now if you're like me, I had heard of Octal. Octal is of course base 8, it's not base 10 or base 16 like hexadecimal or base 2 like binary, it's base 8. So it goes 0, 1, 2, 3, 4, 5, 6, 7, 1, 0, 1, 1, 1, 2, so on and so forth. Now, I'd only ever come across Octal as a sort of concept, and also when it came to giving permissions on Linux. But UKNC PDP-11, they use Octal everywhere. I mean, everything is based around Octal. So we're going to be using Octal to a great extent in these tutorials as well. Now, the assemblers can support hexadecimal, which we would be more used to, and also decimal. But we're going to, when in Rome, do as the Romans do. We're going to be doing a lot of Octal. Now, as always, if you're needing to do conversions, you can always use the Windows calculator in programmer mode. This is the Windows 10 one, but it works just fine in the Windows 7 one. So if you want to have a value in decimal, if we just click decimal here, type in 100, well, we can now see that's 144 in Octal. And if we do 255, you can see that's 377 in Octal. Octal's a bit weird, whereas a sort of a byte would usually split into 8 bits or 2 letters in hexadecimal. It doesn't quite split evenly when you're looking at a 16-bit number. You can't quite see the division between the 2 bytes so easily. But as I say, we're going to have to get used to it to a certain extent. And as I say, when it comes to things like the debuggers, that's what we're going to be using when it comes to Octal. Now, let's get started and let's actually see some stuff in action before I scare you too much with talking about Octal. Okay, so I've got a super minimal example here. As always, we are sort of going to be doing a multi-platform tutorial here, and I've got some includes here to help us out. So we've got a very basic sort of generic file that you could use to modify and make your own program with here. So you can see at the start here, we've just got an initialization, and we're starting at address 1000 here, but that's not 1000 decimal, it's not 1000 hexadecimal, that's 1000 octal. As you see here. So whenever we see a number without any other specification, it's going to be octal. So you need to try and remember that. You'll probably forget, but please try and remember, because as I say, you will come across it. So here's the start of our code, and then we've got an ending of our code, and we've allocated a block of bytes for the stack here, because the stack will start at the end of our program in memory. And as always with my tutorials, if you go to my website, you can download the development tools, this development environment, so if you can call it that, and also the build scripts, because I had to have a lot of help to get them working. So hopefully this will allow you to do some simple programming in either R11, which is the operating system of PDP, or the UKNC, which, as I say, is this Russian home computer, which is basically R11 compatible. So the basic stuff of just drawing text to the screen works in exactly the same way on both. I'll just show you that now. So if I just fire this up here. So here is our R11 emulator here, so it just writes to a console. Now, I believe the PDP-11 didn't really have a monitor, it was no screen at all. I mean, this is a machine from the 70s, and I think it started in the early 70s. So PDP-11, I think, was one of the later versions, but basically it was a console thing, so telnet, if you will. So here we've got the output of our monitor function showing all the registers here. We'll have a discussion about registers in just a moment. But then if I select UKNC here, we'll get something a little bit more colourful. This is the UKNC emulator and it's loading a ROM cartridge. And there we've got the same output hopefully here. And that's running on the UKNC, the Russian home computer now, which is fantastic. Now if we go to debug here, and if we go to debug views, oh, it's got very big. So I just had to tame that window size a little bit. Now all I'm going to show you here is if you look at the numbers here and you look at the numbers here, you'll notice they're a little bit odd. The top of the address space, for example, is 1 and then a whole bunch of 7s, which doesn't really look like anything you'd expect. That's because it's in octal. This is octal, this is octal, these are octal, everything is octal, which is why we're going to be using octal as the primary base for these tutorials, because even though it's a struggle for me, and I'm sure it will be a struggle for you, that's really the way of things in PDP-11 from at every level. That's just the way it works. So if we're going to learn about the PDP-11, we've got to really, you know, just accept octal and try and work with it. Okay, so that's just the basics of loading a program, just to show you I can even do it. So yeah, as I say, download these development scripts. Now, the actual machine itself would have had a display like this. There's an online simulator that runs in Java. It's quite good, but that said, you won't know what to do with it. You have to flip all the switches to potentially byte by byte program the memory. So good luck with that. I have had to play with it. I got it to auto increment a byte of memory, but I'm not really recommending that. But the point I'm trying to make here is these are the settings bits to define addresses or bytes of memory here. And you'll see if you look, they're split into 3s because that is for octal numbers, because octal numbers is made up of 3 bits from 0 to 7 in decimal. So again, I'm just trying to make the point. Octal is the thing, and I've just got a little conversion table here just as a quick reference to point out how octal works with regards to decimal and hexadecimal. And there's also a big table on my website. If you go there, you can download that. But again, as I say, just making the point about octal. Now we can do other representations. We will see those in just a moment, so we'll just skip over that for a second. What I do want to discuss as well, where is it, is the registers. Now as I said, PDP-11 is kind of similar to 68,000 in some ways. It has fewer registers, but it has a lot of similarities to it. So basically the PDP-11 has a total of 8 registers, register 0 to register 7. 2 of these are very special purposes. Register 7 is the program counter. We can't directly use that as such, although it is used in some kinds of addressing mode. For example, in immediate addressing, a value that is stored in the same line as the assembly command is actually using addressing an offset read from register 7, the program counter, because the program counter is the current line. Don't worry about it if you don't understand that. Let's say I'm just trying to point out something that is actually true, even though it's a little bit confusing. The stack pointer is register 6, so you know, you probably don't want to be messing with that too much. And then register 5 is something known as the link register. This can be used to store the return address if you're calling a subroutine, but you can in some cases use it for other purposes as well. So it is a general purpose register, unlike register 6 and register 7, which really you don't really want to mess with at all. But as I say, register 0 to register 4, we can totally do whatever we want with though. Now on the PDP-11, all the registers are 16-bit, so we can actually, you know, it's far more powerful than the Z80 in that respect. Okay, so we've just discussed the very basics of PDP-11 here. Now we're going to actually sort of make a start then, and we're going to be looking at some program compilation as usual. So in the first lesson of each of these tutorials, we start with some very basic mathematics. So we're going to start with some load commands, and then we're going to do a little bit of very basic maths. So let's fire this up. Use the old UKNC here, but we'll get rid of that debug view. I think we'll have it just a little bit clearer. Unfortunately, I'm not sure we can actually make this bigger, but I will try and read out the values on the screen anyway. So, okay, so what we're doing here is we're starting our program. You can see we've got some labels here. we've got a jump command, which will jump to another label. I'm going to assume you've done some kind of assembly before, because this will be a very odd choice if you've literally done nothing in the past. So I'm going to assume you've maybe done a little bit of Z80. I fully understand that the vast majority of people watching this are going to be doing it as a curiosity. Just a bit of a weirdness, which is why I did it, I'm not going to lie. But as I say, I'm going to assume you at least know a little bit, but I am going to try and explain everything to the best of my ability as well. So we've got a jump command, and we're jumping to a label. The label here is loads. Now, there's an important thing about the macro 11 assembler that we're using here. It works with 6-character limits. Now, we can specify longer things, like for example a label or a file name. We can specify 10 characters, but it will actually ignore all but the first 6. This is because of the memory limits of the original machine. Even though it was a server, it was a very early server, so memory was tight, I guess. So they limited it at a fairly adequate 6 characters. So I've tried to keep everything, my file names, to 6 characters. If you use more and there's duplication, you might get error messages. But as I say, generally speaking, if you just make the labels longer, but there's no repetition, it will work just fine. For example, that worked just fine. But then, for example, if I create a second label with the same name, but only with the last character different, because the first 6 characters are the same, I've now got a multiple definitions of a label error message at the bottom of my console here. So and the same is sort of true for file names. You need to, it would be advisable to keep things down to 6 characters. Now, in some cases, like this monitor command, I have used more than 6, but that's because I wanted to make it clear what the function did. I thought it was more important to make it clear this is the monitor tool. So the monitor tool, like in my other tutorials, just shows the state of the registers to the screen. So we're going to be using that to see the state of our registers, and we're using all the registers, even R5 here, because as I say, we can mostly use that for whatever we want. It's just in some subroutines it might be used to store the return address. Okay, so we've got our label here, we've got our jump command that jumps to that label, and here's our first command. We're moving from the left hand side to the right hand side, so we're moving 377 into R0. Well, what does 377 mean? Well, it's not 377 decimal, it's 377 octal, because remember, PDP-11 will default to octal in all cases. So if we type in our well, we don't need to, 377 in octal, 255 in decimal. So there we go. So we're loading value from the left into register on the right here. We're then loading another value here. So we've got this symbol here. I know, so this is the power symbol, but I believe it's also called the caret. I'm not sure on that. But anyway, we use this symbol here, and then we can specify another symbol which will define an alternate base. So in this case, we've done this power symbol and then an X, and that will tell the assembler that the next value is going to be in hexadecimal, which I know is going to be what you probably want, but we're not going to give you what you want. You're going to get what you are supposed to have. So in this case, we're going to make an exception though, and we're going to load in C7. We've got to put a 0 here because the first character isn't a digit, and then we're telling the assembler convert that from hexadecimal, and it will work it out. So in this case, we're loading hexadecimal C7. Well, what's hexadecimal C7? Well, we can work that out if we go to hex here and type C7, and then we look at the octal. It's 307, and I've been very kind here, and I've just noted that just here because we're going to need it when we actually come to see if our code worked or not. So that's going to be loaded into R1 because left is the source, right's the destination. Then we're going to load 1, 2, 3, 4, but you can see there's a full stop here. This tells the assembler that is actually, for the first time, a decimal number. So we're loading decimal 1, 2, 3, 4 into R2. Alternatively, we can use power D as well. That would do the same. That would load in a decimal because X is hexadecimal, D is decimal, and of course you can probably guess B is binary. And you can even do O for octal, which is implied by default in the way that things are currently set up. So we're loading 1, 2, 3, 4 decimal into R2 here. We're loading a letter A because of this apostrophe here into R3. So PDP-11 macro AS is currently beating the VASM ARM assembler because I can't figure out how to get a character in the ARM assembler. So a bit of weird trivia for you there. So that's what we're loading into R3, that letter A, which is 101 in octal. And then we're loading some binary numbers here. Now remember, octal, each digit is made up of 3 bits. So if these 3 bits are 1, then these 3 bits are 0, then these 3 bits are 1. That makes 707 in octal. I believe that one of the reasons octal was sort of chosen for these early machines is because LED displays, they could do 0 to 9, but they couldn't do things like A, B, C, D, E, F. That was sort of too complicated. So it was a way of representing 16-bit numbers and things using the displays that were already readily available. That's what I've heard. I don't know if it's true. It kind of makes sense, but as I say, it's just the way that PDP-11 is. So, and then lastly, we're just specifying octal, even though it's implied in this first part of the code. So let's just fire that up and let's just see the results. So assembler is booting. There we go. So we've got 377 in R0 here. You can see that. That's as we expected. We loaded in the hexadecimal C7 into R1, 307 in octal, and you can see that's loaded. We've then loaded 1234 in decimal because of that full stop, and that's been changed to 2322, which is the octal equivalent. And then we're loading a letter A, which is 101 in octal. You can see that in R3. We're loading the binary, and that's converted to 707. Now we could of course put more binary bits here. We've only loaded a sort of just over a byte's worth here, but as I say, we could have done more. These were all 16-bit registers on the PDP-11. Now in this case we did things slightly differently. We specified move B. The B stands for byte, so rather than loading a 16-bit value, which we've done in all of these other cases, we actually just loaded a single byte here. Now because the PDP-11 is a 16-bit system, it's sign extended that to fill the full register, so it's been signed extended to 1 and then 5 sevens here, and you can see that just here. So yeah, as I say, the PDP-11 is a full 16-bit system. Okay, so that was our first series of tests. So let's just keep this on the top here so we can see it again later. And let's move down to our next set of tests. So we're going to be loading more values of different types, but this time rather than using that power symbol, that caret, and then specifying a letter to denote or using that apostrophe, we're going to specify the radix with a radix command. So we specify .radix and then a number, and then the following digits will be assumed to be whatever radix that is. So base 2 is binary, so that will load 100 in binary. And then we're using base 8, which is just the regular one, that's octal, so we'll be loading 100 in octal. And then we're using base 10 decimal, we're loading 100 in decimal. And then we're using base 16 here, and we are loading in 100 in hexadecimal. Now finally we're converting back to base 8 because otherwise that could cause some problems potentially for the code later on. And then we're running the monitor here. Now you can see if I just scroll up a bit here, now we've got all of the expected values here. 100 in binary is 4 in octal. You can see there's a 4 being loaded into R0 here, and then 100 being loaded in octal here, so you can see that's just there as is. And then 100 in decimal, that's 144 in octal. You can see that just here. And then in base 16, 100 in hexadecimal is 400 in octal. That's a typo, octal. There we go. And you can see that just here. And then finally, we've just shown the monitor, which is the results of this line. Okay, so you can see there that, as I say, we're able to do all of these commands and transfer data in various radixes, as they're called, using either the radix command or by using that power symbol and a letter to denote a certain power temporarily for the next line. Now, with all of these commands, we've typically been working in entire 16-bit words, but we can also work with bytes, as we saw earlier with the move B command. We've been moving values straight from the immediate values into the register here, but we can also work with register to register, of course. You'd certainly expect to, and it's the move command again that does that. So in this case, our source is R4. We're moving R4 into R0 here, and then we're moving R5 into R1, but this time we're only moving the low byte. And then here, as well as moving, rather than moving a 0 into a register, if we want to 0 a register, we've got special commands to do that. We've got clear commands, so we can clear R4, and here we're clearing the low byte of R5. And so let's have a look at the results there. So R4 used to equal 707, and that's now been transferred to R0, so R0 is now 707. R5 used to be 1 and then 5 sevens here, and that has now been transferred to just here. R4 used to equal 707, we used the clear command, so that now equals 0. And R5 used to equal 1 and then 5 sevens. We use the clear command, but only at the byte level, so only the bottom 8 bits have been changed. So that has become 1774. The reason being that that 4 digit is kind of split between the low byte and the high byte. Remember, 3777 is the maximum byte value in octal of a single byte. So as I say, it's a little bit tricky, I know, but as I say, we've really got to work in octal if we're going to do PDP. But as I say, when in Rome, so I guess when in PDP, you've got to use octal. So anyway, so that's our loading. Let's have a go with some increment and decrement commands, which of course we do have. Okay, so here we're going to do some incs and decs. So we're loading the value 254 in decimal into R0 here, which is 376 in octal. And then we're doing some incs here to R0 and some decs to R0. Each time we're going to show the value in R0. And then we're going to do the same again. We'll load 254 into R0. This time we're going to do incs and decs only at the byte level, because of course by default it's 16 bits. And we're going to show the result each time. And then finally, rather than incs and decs, what we're going to do is we're going to add 100 in octal to R0, and then we're going to subtract 10 in octal from R0. So as well as the incs and decs, which of course are just by 1, we can also just add and subtract arbitrary immediate values. Okay, so let's just fire that up and we'll see the results of all those commands here. And so here it is. So you can see here that we loaded in 254, which is 376 in octal. So that's our first value here. We then added 1, which went up to 377. We then added 1 again. Now the limit of an octal digit is 7, so it rolls over to 0, and the next digit along will also roll up, because that was also 7, so that went to 0. So the 3 then became a 4 here, so 400 is our new octal value. We then did some decrements, so it went back down to 377 and 376. So that's the 16-bit inc and dec. When we did the byte ones, now 254 is almost at the limit of a byte. So the first inc went the same, it went up to 377, which is 255, the limit of a single byte, of course. And so when we inked again, it rolled over to 0. Because we're working in bytes, of course, even though these are 16-bit registers. Then when we decremented in bytes, that rolled back in the opposite direction, going back to 377 and then back to 376. Now, when we did add and subtract, 376 became 476 because we'd added 100 in octal. And then we subtracted 10 in octal, so 476 became 466 just here. Okay, it's all entirely logical, to be honest. The commands may be slightly different. This inc B isn't quite what you might see in other systems, but apart from that, it's really just the octal that's the surprising thing about all this. Okay, now in those cases, we've been doing stuff with just immediate values and registers. We're going to look at addressing modes next time in a great deal of depth, but just for now, I'm just going to point out we can, of course, work with direct memory addresses. So we're defining some test RAM just here. We've got a little memtest function, which I often have in my tutorials here. And what we're going to do is we're going to dump the test RAM to screen. We're going to load in a value into a register, and then we're going to load that register, remember the source is on the left, destination on the right, into the address test RAM, into the address at, you see this at symbol here, and then test RAM just here. So the at symbol here is specifying an address. So rather than test RAM being an immediate value, test RAM is now becoming an address, which in this case, because it's on the right, is the destination of this move command. So let's just fire this up and hopefully we'll see that in action. Okay, so the first line here you can see is all zeros because our RAM was initialized to zeros here. We've got to make sure we're word aligned because, like most systems, a 16-bit system, it wants to be word aligned. So we are loading in then 1, 2, 3, 4, 5, 6 into R0. Now I haven't shown that to screen, but what I have done is I've loaded the value from R6 into the address at test RAM here, which of course is what was shown to the screen, and you can see that's been loaded in just here. So we've actually changed the memory that we defined just here with this move command because of that at symbol. We're going to go into this a lot more next time. As I say, this was just to give you a brief introduction, just to get you started and see a few of the simple things that the PDP-11 can do. The final thing we're going to do is we're going to have a look at a very simple subroutine test. Now, we've got a very common command, JSR here, which you will know from the 68000 series. It's slightly different on the PDP-11. This is a bit more of a sort of RISC thing. We actually specify a register as well as the address to call to. Now, on some RISC systems, you would specify a register which would store the return address. The PDP-11 is a little bit odd in this case. What you actually do is you specify a register that will be pushed onto the stack. So in this case, we're specifying that the program counter should be pushed onto the stack. So what we're doing here is effectively, this is just a standard call to a subroutine. This is the sort of bog basic one, if you will. So what we're doing here is we're just calling the subroutine new line, and we're using the program counter for that call. Here we're calling sub1. You can see sub1 down here, and that is going to push the program counter onto the stack, the program counter as it currently is here. And then our return command, in this case, we've used an RTS and program counter, which says return from the subroutine and pop the program counter off the stack. So that's what we're doing there. We've then got this call command. Now, you might wonder what that is. Well, it's basically a macro. I haven't defined it. The assembler sort of knows it. And what this says is the same as jump to subroutine with program counter. That's kind of the basic one. And we're calling T1 again. Now, the equivalent opposite of that is a return command, which is the equivalent of RTS program counter. So generally speaking, you'd probably just want to use call and return. They'd be easier, but I'm not trying to make things easier for you. I'm trying to explain how things really work, and that is how they really work. So that's what the process is actually doing. Now you might think, well, why are you specifying this program counter onto the stack all the time? What's the point of that? Well, rather than putting the return address straight onto the stack, we can actually put the return address in an alternate register and push the original value of that register onto the stack here. And that's what we're doing here. So what we're saying with this command is saying push R4 onto the stack and then store the return address in R4. And this is more like what the RISC processors usually do. And then we call this subroutine here. The reason we might want to do this, and we're not doing it in this case, but the reason we might want to do this is if we had parameters that were being specified in line after this statement, then we've now got the return address already in R4, so we can read in from those alternate values and then use a return with that R4 to return to the new address after we've added a few bytes to that return address. If you don't understand that, don't worry. It's, as I say, it's just having done that kind of thing in other assembly languages, you look at this and you think, hey, this is something you could really take advantage of. But as I say, at this point, I'm just trying to explain how the JSR command does differ slightly from other systems. And don't worry, because it's not something you're going to really need very much, and we'll go over all this kind of thing further down the line anyway. So let's fire this one up and let's just check what happens accurately represents what I've just described. Maybe it won't. Okay, let's just fix this on top. So here's our subtest. And the first thing we're doing is we're calling sub T1, which has printed a character A to the screen, and you can see that's first there. Then we've called sub 2. Sub 2 has printed a B, and you can see that just there. So these are happening in order, and obviously they're returning because they are executing. And then sub T3 here has printed a C, and then it's left a space, and then it's printed this just here. And now this is a dump of all of the registers here. So you can see R4 equals 1264 here. Now in this case, the R4 value here has actually taken the return address of the calling routine, so it would effectively have been this line just here. Now when we ran the monitor here, the R7 equals 1274, which is a few bytes after this. As I say, when we specify an alternate register here, we're actually using that as the return address. But generally speaking, this isn't going to be something you're going to need, and if you're just getting started out, then you're going to be best off really using the call and the return statements instead, just to make things a bit easier for yourself. But as I say, I like to make it clear what's going on, because programming such an old system as this, you're not probably going to want to create any new games in it. As I say, the UKNC is a fascinating machine. I'm going to be having a look at that more later once we've gone over the basics of this. But as I say, generally speaking, I'm intending this tutorial as being for people like myself. I'm 41 now, so it's a system that I was too young to use in the day. It's not something I've ever come across professionally, and honestly, I'd never even been aware of it. It was kind of a system I'd never even heard of, so to speak. I probably had heard of it, but it just skipped me by. And so I was fascinated to see just how advanced it was, and see some of the design choices they made. And if you're watching this, I hope you're finding it interesting as well. Anyway, if you like this kind of thing, please like and subscribe, because it helps with the Google algorithms. YouTube ranks the videos by how many people watch them and how people like and things. So if you want to see more of this kind of thing, please do that. We're going to be doing a whole series of these, because I'm crazy enough to do old tutorials on obsolete machines. And so if you would like to see them, please stick around. Anyway, thanks for watching today and goodbye.